A random variable x is said to have a double exponential function if the density of x is given by 1/2 beta expected value of minus absolute value x minus alpha over beta with a parameter of alpha and beta, where our alpha is greater than negative infinity and less than positive infinity. So when we want to get the mean, we have 1/2 beta with expected value of negative alpha minus x if our x is less than alpha, and we have alpha when we have this negative x raised to the power of beta minus alpha if our x is greater than our alpha. So given this equation with this equation, we have this one. So 1/2 beta e raised to the power of negative alpha over beta x e over x minus x over beta dx, which integrated from negative infinity to alpha, plus e to the power of alpha over beta x e negative x over b dx, integrated from alpha to positive infinity. So we will integrate this part, and we have this one, the u du, b d and dv and the v, and we arrive in this one because of the ub minus integration of b du. We change x with the alpha, we have this answer. And in this part also, we will integrate it by parts like we did earlier. Given this, we cancel the negative b squared and positive b squared since they have different sign. And if you will ask which it comes here and here, and so we have 1/2 beta minus 2 alpha beta. We have to divide this one with this one, so we have our mean, which is equal to alpha. So now we will get our variance. In getting the variance, we have ex squared minus x to the power of 2 minus alpha raised to the power of 2. So given the equation, like the equation here in our last getting the mean, so given with this equation, but it has an x squared. So since our variance is x squared, so we have this x squared, and we will integrate it by parts like we did another in getting our mean. So in this part also, we will integrate it by part. So given by the u v minus integration of b du. Combining the two, and this one, we arrive with this answer. So combine again, and we have alpha squared plus 2b squared plus alpha squared plus 2b squared. So we have 2a squared plus 4b squared. We have to divide it this one, so we have a squared plus 2b squared remaining. But don't forget that we still have our negative alpha squared here, so we will minus here. So we have the equation a squared plus 2b squared minus a squared. Since they have different sign, cancel, so we have the remaining 2 beta squared, which is our variance. So this is the variance, and this is the mean of double exponential function. A continuous random variable x has a Weibull distribution with parameters a and b if its density function is given by abx to the power of b minus 1 e negative ax raised to the power of b with an indicator 0 and infinity x, where e is greater than 0 and b is greater than 0. But if b is equal to 0, the Weibull density is reduced to exponential density. And to prove this one, we have to get the mean and variance of a Weibull distribution, which is in a Theorem 6.3. So by getting the mean, we have integrated from negative infinity to positive infinity function of x dx. So we have here x evx raised to the power of b minus 1 negative ex raised to the power of b integrated from 0 to infinity, which is given here in this density function. And we will have this one, we have to change this one. So ex to the power of b here will become t. X is t over b, a 1 over b. Then abx to the power of b minus 1 is equal to dt. So we will change this one with this one. So we have x is equal to t over e raised to the power of 1 minus over b, e, and then e t negative t. So we get the mean. We have this solution. We have this proving which is the mean of the Weibull distribution. Another is getting the variance. So variance has ex squared minus ex squared with MGF of x squared ebx b minus 1 e raised to the power of negative ex raised to the power of b dx, which is integrated from 0 to infinity. We will change the x squared with this, like in this one, and so on. We have this one. So we have now our variance. And this is the variance in Weibull distribution, and this is our mean in Weibull distribution. That's all. Thank you.